In the last session, we discussed the general procedure of how to solve differential equations with linear coefficients of the general form. Now let's study some examples. So the first example would be the following differential equation: u prime prime plus x u prime plus u is equal to 0. We impose boundary conditions. We normalize both of our solutions at 0. We require that they equal to 1. Also, we require that our solutions at plus and minus infinity are bounded functions of x. In fact, we require that they vanish. And in addition, we require that one of our solutions, for example, u2 of x tends to 0 at x tending to plus infinity in such a way that the following limit is constant. So that means that u2 of x behaves like 1 over x when x tends to plus infinity. So let's see if we are able to single out that kind of particular solution. Right. So the first step is to write down our p and q polynomials composed of the coefficients of this equation. Right. So let's actually write down these all of our coefficients. a2 is equal to 1, b2 is equal to 0, a1 is equal to 0, and b1 is equal to 1, and finally a0 is equal to 1, and b0 is equal to 0. Right, so here is our p polynomial, and it's equal to t squared plus 1. Q polynomial is simply t. Now we perform the integration p over q, which is simply t dt, which gives us, so it's t squared over 2 plus log of t. And finally, we write down our functions, which fix the structure of our solution. So z function is e2, as you remember, p over q dt 1 over q, which is e2 t squared over 2 times t over t. So it's e2 t squared over 2. Right. Now v function is basically z function times q and times e2 xt. So it's simply e2 x t plus t squared over 2. Right. So, okay. And v function is the following thing, multiplied by t. So now we are ready to actually try to figure out what the contour of our contour integral is going to look like. So first of all, our solution itself. So u1, 2 of x is equal, as you remember, some contour integral e2 xt times z of t dt. Right. Now z of t is this function, and the contour should be chosen in such a way that the function assumes identical values at its endpoints, right? So the most obvious choice would be probably some kind of closed contour. Obviously, if the path is closed, then v function assumes identical values at its ends, because it's a single-valued function, so it's okay. But the problem is that function z of t is an analytical functions in a complex plane. In particular, it's analytical inside this contour. And as a result, the integral can be computed as the sum of the residues inside this contour, but there are no residues. The function is analytical. So the solution is going to be just trivial. It's just 0. So this is not the solution we are looking for. So in this case, it's quite obvious that we should choose a different contour. It should have open ends. And now the question is where we should position that open ends. Right, so the most probably obvious, the easiest points to find for these v functions are the points where this function, v function, vanishes. For example, we noted that if t is equal to 0, then v function is equal to 0 as well. On the other hand, we may easily find the whole regions in the complex plane where v function also vanishes. For example, just look at this exponent. It has two terms, xt and t squared over 2. If t is large, then the exponent is dominated by this quadratic term. So if we require that t squared is negative and large, then v function vanishes regardless of the value of x. X may be negative or positive, whatever. So what we require is that we seek for the distant regions in a complex plane of the argument t such that the real part of t squared is negative. All right? So let's actually solve this elementary trigonometric equation. So t is equal to rho to e to I phi, and the real part is going to be proportional, the real part of t squared is going to be proportional to cosine of 2 phi. So cosine of 2 phi is negative. All right. So now, and the solution is 2 phi. 2 phi is stretches from pi by 2 to 3 pi by 2 plus 2 pi n. And these are our regions. Phi changes from pi by 4 plus pi n till 3 pi by 4 plus pi n. So let's plot these asymptotic regions. Well, first of all, these are asymptotic regions. They are valid only for rather large t. So t should be much greater than x because the second term should dominate over the first one. Okay, so let's sketch the borders. So this is pi by 4, and this is 3 pi by 4. So this is our asymptotic regions. So this is precisely the area where the exponential function decays, right? So and plus pi, so there is another symmetric region in the lower complex semiplane. Pi by 4. So now what we should do, so for example, can we choose the contour like this, for example? So it starts at infinitely distant point and ends at the same allowed region. Well, it happens that we can't. Why? Because you can deform contour in any arbitrary way, in any way which you wish. The only condition is that you shouldn't cross the singularities of your integrand. But z of t doesn't have singularities, so what you can do is you can shrink the contour in such a way that it will be positioned entirely at infinitely distant region. But at this region, the integrand z of t, which defines our solution, vanishes because it's proportional to the same exponent, e to t squared over 2. So because of the possibility of this deformation, it will yield us trivial solution. So that kind of contour is no good. So what would be the other choice? Well, for example, we can choose the contour which starts at one allowed region and ends at the other one, like that. Then it can't be deformed so like that, right? So always there is a piece which goes here, so where the integrand is significant, so it doesn't vanish. So that kind of contour will yield us finite non-trivial solution. So we'll call it C1. And the other possibility would be the contour. For example, we mentioned before that v function vanishes at point t is equal to 0. So why don't we just start our integration path here and stretch it to infinity in the upward direction, like that. So that would be the second possible contour. So now we have two linear independent contours. Both of these contours, they can't be smoothly deformed into one another. So they actually define two linear independent solutions of the second order differential equation.